Is there anything left over from the test or anything before I get into new stuff? Oh, shit.
So we just had one more test.
Yeah, one test and one final exam. Yeah. Somewhere in there, maybe at least one quiz. I'll tell you about it. Obviously, I don't do pop quizzes yet.
Let's say we do well on all the tests, but we bomb the final, do we still pass the class?
Well, it depends on how your average comes out, don't it? Right? I can't possibly answer that question. It depends on how your average comes out.
That's how I'm asking you.
Well, no, I'd have to have some specific numbers to work with. You see what I'm saying? How bad is bad? Where are you now? Where will you be before you take the final? Do you see what I'm saying? The higher your grade is now, the less you're going to need on the final. So very often I'll go into a final and there are some people that need to make like -7 on the final to fail. Right? Now obviously they're going for like an A, maybe even A+. But they basically have to hit me with their car on purpose. You know, that's how you get a -7 for me. Bam! That's -7, you failed. But do you understand what I'm saying? Because they have such a high grade going in, the final's only 25%, and that sounds like a lot, but you're going in with 75% of your grade set. And the final is the heaviest weighted thing, but against that, it's actually 1/3 as much. I mean, you guys get that? 75% is 3 times as much as 25%. Yeah.
So, like, if you have a T, like you have an N, you fail the test.
If you have a who?
A B.
A B?
Yeah.
Okay.
We'll be fine. Pass the class.
Yeah, all right, let's see. Now watch. So watch this. You ready? So if you have let's say you have an 80, that's the lowest B possible, right? Let's pretend like you got an 80. Going into the final, which means that's like 75% of your grade is an 80, right? And now you're curious, what can you make on the final? I know you guys are like, come on, Jeff, just tell me.
Yeah.
You following me so far?
Yeah.
75%. Going into the final, 75% of your grade would be an 80. I don't know what I'm going to make of the final because, I don't have that power. But I know whatever I make is going to be 25% of it. And I want my average to be a 70 so I pass, right? Oh, shit, I got to solve for X. Oh, shit. Algebra happens in the real world? No freaking way. Right? Obviously, I could do this thing, but I make my Excel spreadsheet do it for me. Right? Now, a lot of people take that to mean, well, then I don't need to know this shit. I'll just have my Excel spreadsheet. No, we're the freaking humans. We should know the shit that the thing is programmed with. We should. We shouldn't be servants to our technology. And I don't care if you agree with me or not. It's what you need to do to get a degree. You don't have to do this shit if you don't want a degree. So that's your decision to make. So let's see if we can figure this out. What is 80 times 0.75? What is 0.75 as a fraction? You should know this. 75% is 3/4. I mean, normally that's something that most people kind of know. Do you see how, now please, do you understand? I could just do this in my calculator, but I want to show you how I do stuff in my head. That is 3/4. 4 goes into 80. I mean, 0.75 is 3/4. They're the same number. They're the exact same number. 4 goes into 80. 20 times 3, 60. Then over here I got plus 0.25x equals 70, right? Plus 0.25x equals 70. How do I solve for x? Subtract 60.
And change the
0.25x equals 10. Divide by 0.25 now. How do you do this? Watch.
Only one will change the. Only one.
Yeah, watch. If we multiply by 4, the bottom becomes 1. So it's 40 divided by 1, which is 40. Or just 10 divided by 0.25 in the stupid little calculator.
So 40.
So what is that again? That would be the grade I could make on the final and still pass. Do you see what I'm saying? And even then, it's still even better than that because I don't know if you remember on the syllabus. All right, what happened? Some of you guys are looking at me like...
Everyone's comparing their own grade to that probably.
But see, that's basically how I figured out this. It's just that right now you don't have 75%. You have more like 55% of your grade set. So that was 55 and that would be 45, blah, blah, blah. All right. So that seems like a simple question, right? Like, what would I have to get on my final? But that's algebra, because if I knew what it was, I could just do that directly. But I have to do it backwards because I don't know what it's going to be. So I love that question because that's just another example of algebra actually is useful. It is. It helps you when there's a part of a problem you don't know. Okay.
How many problems is usually the final?
Well, you know, how much time do we have for a regular test? Almost 2 hours. How much time do we have the final? 2 hours. 2 hours. I don't know. Apparently you guys don't know that. You guys know that? You guys know that now. We have 2 hours for a final exam. So the final actually cannot be that much longer than a normal test, right? So exactly what's going to be on the final, you'll find out when you take it. Ha! So you have to know everything, and then I'm going to have to pick and choose. I'm obviously not going to be able to put everything on there, but you're not going to know until you get it what the hell's on there. Yeah.
You're not going to do it for free.
No, of course I am. Yeah, practice final, answer key. Sure. I don't know how much good that's doing, but I'll keep doing that. Yeah. Apparently it's helping some people out. Some people do exactly what I tell them not to and just look at the answer key and go, yeah, that's what I would have done. And then they die on the test because they built up false confidence. And that's almost making me not want to do that anymore. Yeah.
I have a question. For this homework, I looked on the little thing here, and it doesn't say like every third, every fourth, every fifth, like the first 7.1.
Oh, the guy.
Yeah.
Yeah, 1 through 17.
That means do all of it.
Yes, that always means do all of it. All of you guys, there's like one that says 1 through 8. And some people did 1, 4, 7, and they were like, what's this 8 thing, Jeff? You should know math. No, 1 through 8 means 1 through freaking 8. If I don't say every third one, I mean every one. I shouldn't have to say every one. That should be the default. So yeah, 1 through 17 means 1, 2, 3, 4, 5, 6, 7. I like it though. Good question. But that's happened earlier in the homework, also where it didn't have anything on there. It just means do every damn one of them. Yeah. I hate when you guys are so mean to yourselves. You do every one of them when I said every third one. All right, it's extra practice, fine. All right. Anything else before we get into new stuff? Okay. All right.
That's our problem. Who's going to get it? Really good review.
Oh, anybody come in after I gave these out? Has everybody got a copy of the chapter 7? The first few sections out of chapter 7? Okay. So this is going to involve, part of this is going to be properties of real numbers. So like, I don't think we've talked about, have we talked about commutative property, associative property? Not yet. Does that sound vaguely familiar?
No.
There's also distributive property. We have talked about that. But they start off with rational and irrational numbers. So, what's the root word of rational? What's the root word of rational? What's the ratio? I love it. So, rational numbers are anything that can be written as a ratio, a fraction, right? So, examples of rational numbers would be actual fractions. That's just crazy. Can this be written as a fraction? Yes, it is a fraction. What about 0.72? Is that rational? Can you write this as a fraction? As a ratio of whole numbers? Yes. It would be what?
72 over 100.
72 over 100. Right? Tenths, hundredths. How are we doing so far? Again, some of you guys are looking worried, but this isn't any big. This is what the word rational numbers means. It's what that phrase means. It means any number that can be written as a ratio, as a fraction of whole numbers. Now here's one that's a little bit weird. So any whole number obviously is 7. Is 7 over 1. So that's definitely rational. Well, real quick, what would be not rational? What's irrational? Well, that would be like square root of 2. 1.414, blah, 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 blah. What other number kind of does that? no pattern to it. It just goes forever. Some decimal that goes forever. Some special number that maybe deals with circles. Pi. Pi 3.141596, blah, 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 blah. That's as far as I'm ever going to remember. I got too much other shit to remember in my brain already. All right, stuff like that. Those are numbers that the decimals never repeat. They never stop. Decimals that stop, I can always write that as a fraction. Always. Even if it was 0.1, 2, 3, 4, 5, 6, 7, 8, 9. That's a fraction. I can write that as a fraction. I want you to notice something. 0.1 is what is a fraction? 1/10. 0.12 is what is a fraction? 12 over 100. Do you notice there's 1 0 and there was one place? There's 2 zeros and there's 2 places. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? It's already counted for me, but still. So there's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. Yeah. Stop there. Are you guys understanding what's happening? Of course, every place is well defined. If I go really far out, it's going to be kind of a gross number, but we can construct it easy. What are you all right? She's like, right? Because 2 places out, that's hundreds. 3 places would be thousands. 4th place would be 10,000s, right? So forth. Okay, how are we doing? So as long as the decimal stops, it definitely can be written as a fraction. The bottom might be really freaking big, but it's still a fraction, right? Fractions don't say, I gotta be small. No, fractions can be a ratio of whole numbers. And how big can the whole numbers get? Really freaking big. Now there's one, I can't remember if I showed you this. This is kind of cool. Stay with me now. I don't think you've seen this yet. This one we should all know. 0.333. I'm pretty sure I did this before with you guys. 0.33 repeating. You guys, most of the time people know this. What would that be as a fraction? Does anybody know? No. Third, yes. 3 over 10 would be 0.3. 0.3 forever is 1/3. And of course, you can verify that very quickly. 3 into 1 would be 3, 9, minus equals 10. 3, 1, minus equals 10. 8, 1, minus, oh my God. All right, so 3 forever. Okay, that was an awesome explanation. If you try it on your own, you'll get a bunch of freaking 3s. So the key to that is any decimal. Oh, see how slowly I'm talking now, so it's probably a note. Any decimal that stops or has a pattern like this is rational. It can be written as a fraction. These don't stop, and they have no pattern.
So even if the pattern is 1, 2, 3, 1, 2, 3.
Yes, beautiful, exactly. Even if the pattern is 1, 2, 3, 1, 2, 3, 1, 2, 3. It's got to be some kind of repetitive. It could be any size chunk, but the chunk's got to repeat. Yeah. There are people that are hoping that pi actually repeats eventually. Maybe the first 10 trillion numbers repeat or something, but I don't think so. But they hope a lot of things. Okay, how do we feel so far about this? That's the difference between rational and irrational. It can be written as a fraction versus they can't be written as a fraction. Now this, if you did this, I don't care. Is that a ratio of whole numbers? No. Rad 2 is not a whole number, so that's not a fraction. Yeah, I like it. Maybe. Okay. So let's see, what else can we do with this stuff? Let me take some stuff right out of there. But there are some rational numbers that you got to be a little careful about. They don't look like they're rational. So for example, square root of 36, is that irrational or rational?
Rational.
Why is it rational? Because square root of 36 is 6. So why is the square root of 2 irrational? Because square root of 2 is, I don't know. You guys, yes?
I think I'll wait. If you put the, oh no, that one, never mind.
Okay. All right. I have no idea, but I'll go. So don't just look at the radical, the square root sign and say, oh, it's irrational. If you can actually do it and it comes out nice and whole, then that's going to be rational. Or even, square root of 49 over 25, which threw some people off on the test. But what's the square root of 49? 7. What's the square root of 25?
5.
That is a fraction, so that is a rational number. All right, let's see. Oh, okay, okay. Oh, yeah, they're a little evil. I like it. All right. So I'm looking at the homework to make sure that if there's anything freaky in there. I like this question from earlier. I can't remember if I showed you this, but let me see if you guys can go with me for a second. What sucks about this number is, of course, what this means. What does this mean again? It just goes forever. So I can't really write this number. I have to just put a bar over there and say, keep going like that. That's what the number is. Leave me alone. But I'm not going to write the whole damn number out. Let me see if you guys can get this. This is the one you gave to me earlier. So what is this as a fraction? I don't freaking know. But Jeff just said it can be written as a fraction. It's got to be. Because it's got a nice chunk that repeats, right? Here, the chunk is just one number. 3, 3, 3, 3. Here's 1, 2, 3, 1, 2, 3, 1, 2, 3. Nice little waltz going on. So, what is this as a fraction? Do we know? No. So, let's call it x. Damn. That was a neat emphasis on that. Let's call it x. Let me see. This is kind of cool. This is not something I would really doubt if they made you do this yourself. It's a little bit freaky. No. Okay, good. But they do make a point. I want to show you this anyway. I'm about to show you something that you don't have to be able to do yourself. Which either people are going to tune me out or they're going to not have heard me and think this is going to be on the test. But if I multiply this by 1,000, just go with me. Just do it and see what happens. If I multiply by 1,000, what happens when I multiply a number by 1,000? The decimal moves over 3 times. Because every time I multiply by 10, it moves over once. So multiply by 1,000, that's 3 tens. It's going to move over 1, 2, 3. So now this is going to be 123.123 forever. Now imagine, if it would have been 1, 2, 1, 2, 1, 2, I would have multiplied by 100. Do you see what I'm trying to do? I'm trying to line up this freaking infinite shit. Right? The infinite part of this is what makes it hard. So watch what happens when I subtract these now. What is 1,000x minus 1x? How many x's do I have? 999. Jeff, there you go. 123 minus 0 is 123. That's amazing. 0.123 forever minus 0.123 forever is cancels. Can I solve for x? Yeah. So x equals 123 over 999. Which you can divide by 3. Can you guys see how I know that? 1, 2, 3 is 6 when you add all the digits. So 3 goes in. So this will be 41 over 333. Now try it. If you have a calculator, do 41 divided by 333. Good. A few people are trying it. I like it. Could even be your phone right now. What do you get?
0.123. 1, 2, 3, 1, 2, 3.
It shows you that as long as it can, and then it says, trust me, it keeps going. Right. So the screen is only so big. Right. You don't want the screen to become bigger and just go into the next room and kill people. That'd be horrible. What a way to go. Taken out by a calculator. All right, do you guys, you could do this. It's not a trick. I was about to say this trick. It's not a trick, but you could do this with everything where a packet repeats. You could do this. That's why if it's repeating, it's rational, because I can write it as a fraction. Okay, so like 0.23, 0.23, 23, 23, 23. I could do this thing. I would multiply by 100, because I don't have to move it over twice now, and the same thing would happen. It would be writable as a fraction. So all you have to know from this, you don't have to be able to do this on your own. I think some of you maybe could. You just have to know if the decimal stops or if it has a packet that repeats, it will be rational. Right? So you're going to have a few of those problems in the homework. So what about this one? Is this rational?
No.
Obviously not. Right? There's a pattern to it, wouldn't you say? But isn't there a pattern? 42, 43, 44?
Oh, yeah.
Right? There's a pattern, but is it the right kind of pattern? Is it a repeating chunk? No, there's no chunk that repeats. So be really careful when I say a pattern. I was really careful by the way I said that. It's got to be a repeating pattern. It's got to repeat the same thing over and over again. Maybe. So there's another one would be point 1 2 1 1 2 1 1 1 2 1 1 1 1 2. Oh, that's a freaky one. Right? Math people are all geeking out about this, but is this rational? Hell no. Is there a packet that repeats? No, I see 12 and then 112 and 1,112. There's not a packet that keeps repeating. You guys see the difference between this and this? Here, there's a definite. Could I put a bar over something here?
No.
Hell no. Because it's going to be a different number of ones in the next if it keeps that pattern. There is a pattern, but it's not a repeating pattern. So that's not good. Okay, maybe. So there are going to be a few homework problems that actually give you something that look like this or this. And you have to say is it rational or not. Those are totally irrational. They don't have a repeating pattern that will save their ass. Too bad. Let me see what else they throw at you here. Blah, 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 blah. Blah, blah, blah. Oh, do you guys remember the difference between whole numbers and integer? What number did the whole number start at? The number that looks like a whole, right? So what are the whole numbers? 0, 1, 2. But what do the integers add to that? Yeah, the negatives. So if I said, is this a whole number or an integer? That's an integer, right? Because integers include the negatives. So integers adds the idea of negatives to the list of whole numbers. I like it. All right. So it's going to be a little bit of a, and that's kind of a repeat. We talked about this earlier this semester, so they kind of bring that back now. Cool. There's really not that much in that first section. I like that. Sweet. First section, very short and sweet. Gotta like that. So all that's in the first section is, can you tell the difference between a rational and an irrational? Right? So if I said square root of 7, that would be irrational, because I can't do the square root of 7. But if I said square root of 25, because square root of 25 is 5. Okay. Okay. Sorry, you just look sad. Didn't mean to point you out. It's the lot of the math teacher. I just get to make people really sad all the time. Okay. So we're about to get into these properties, and they basically never leave you alone once you start to talk about them. One of them we know already, the distributive property. All right. Let me go back over that. I'm pretty sure we talked about this before. This idea of how to do this. Have we talked about that? Maybe not. I feel like maybe we have.
That's distributive property.
See again?
Distributive property.
Exactly. Why does it work? Officially, what would order operation says must be done here?
Parentheses.
Yeah, so what's x plus 2? Please don't say 2x. I want to save you from yourself real quick. That's totally different, right? X plus 2 is adding them. 2x would be multiplying them. Addition cannot become multiplication. That's like water into wine, which would be a much more useful skill. So this, I can't follow my normal order operations. I don't have to break any rules, though. So distributive property, if you really start to look at it, it looks like you're breaking rules, because order operation says do in here, and distributive property says screw you. But watch this. Help me out. Without using the word multiply or multiplication or times or anything related to that, what does that actually mean? That's how you read it. What does it mean? That's not what it is saying. Don't use anything related to multiplication. You're like, what the shit does he want from me?
The product of 2 and x? No.
See, product is related to multiplication. 2x is doing what? 2x is doing what? Adding. All right. All right, once I write that, you guys, what's x plus x? 2x. All right, so 2x means 2 of these adding. So 2m would mean m plus m. It's amazing, right? 2z would mean z plus z. Are you guys with me? Yes? And real quick, while I'm talking about this, that's when I put a 2 up here, No. When I do, this means two of these multiply.
Right?
So coefficients are based on addition. That's why they play well with addition. Exponents are based on multiplication, and that's why they will play well with multiplication. This would mean x times x. All right, maybe. So really a lot of math is just shorthand to communicate ideas very quickly, right? So if we put a 2 there, it means something. If we put a 2 up there, it means something else, right? Which is really, actually, if you look at it, it's a pretty good way of doing things, but as us that weren't there when they made it, we got to kind of catch up with what the hell they were talking about. That's okay. So what's it got to do with this problem? Well, I have 2 of these. 2x is x plus x, 2m is m plus m, 2z is z plus z, 2x plus 2 is
4.
no, come on, help me. Right?
2x.
2 of these is this plus this. 2 this is this plus 2 this is this plus this. Do you see how it follows the same pattern? What's twice Jeff? Jeff plus Jeff. Some of you guys are like ones and up things. Right? Right? That's the pattern. 2x, x plus x. 2m, m plus m. 2 this plus this. So that's what the coefficient means. So a way around order operations is to use a more fundamental idea and say, well, a coefficient means that. And then how do I add these? I just, x plus x is 2x. 2 plus 2 is 4. Now, real quick. I know somebody somewhere is going to yell at me, why the hell would you do all that shit? But what am I doing right now? I'm explaining why distributive property works. I'm not telling you, do it like this now. Good heavenly Lord. No, don't do this shit. 2 times x, 2x. 2 times 2, 4. Why does it make sense? Because I would get 2 of them, 2 of each. Sorry.
I was just gonna say, why don't you boil it?
Oh, I got you. That's why. I was explaining why what we're going to do works. So never do this. Oh my God, it would so suck if I gave you this problem here. And I get somebody that's like, why minus 5? Why minus 5? Why minus 5? Because why minus 5? Because why minus 5? And you know that should be. Of course, now I can just use the actual property, the distributive property, and that's one of the best named properties ever. If I could just spell it, distributive property, because I actually take the 80 and distribute it. So I would get what?
80y.
80y?
Minus
80 times 5.
80 times 5?
minus 80
It's
80s.
That's a 5.
250.
5.
That's a 5.
250.
400.
400.
400.
There you go.
I will say yes.
This is my yes, and this is my 5. Right.
Know the difference.
5, not the best number for me. All right, so most of us know the distributive property. I don't know if you've ever shown why it works. You should always want to know why something works. Because if you know why it works, you can remember it better. And you'll buy into it better. Instead of me just saying, do this, you'll be like, oh, that's just the freaking way it works. So of course I'm going to do that. Okay. So, what about... let me give you some concrete examples of this. Now, if I had this problem to do, I would hope that nobody would distribute, although if you did, technically you'd be fine. Because what can I do here?
5 plus 3.
Yeah. So one way to do this is do 4 times 8, which is 32. But distributive property will always, it has to always work. I just don't always have to use it. I only have to use it if the things in here are not like. I can't put them together. But it still will work. What's 4 times 5?
20.
20. Become a 0. 4 times 3? 12. 20 plus 12? 30 freaking 2. Yes.
If you would have added the parentheses and added 8 times 4, you would have got the same thing also.
Added the what?
5 plus 3 and then multiplied by 4, you would have got
That's
the
what
same
I did.
That's
this.
Oh, yeah.
That's all right.
Here to do.
But you're right.
But you're right, exactly. That's what's more important is you're right. Let me show you this. Here's a little trick. Well, all right. We got to hold off on that. We'll come back to it. It's a little too early to show you that trick. Blah, blah, blah. All right. So let's get to the other properties. So that's distributed property. It always works, but there's only certain times that I have to use it. Let's talk about commutative. And associative. Yeah, I'm going out of where's to it. Distributed property, I think we would have had more connection to it. These two are just a little bit weird. Because effectively these two say, well, let me ask you this. Does it matter if I do 7 times 8 or 8 times 7? Are those different?
No.
No, so that's commutative property. Multiplication is commutative. What did we do? If you travel to school, you are officially called a commuter. You've all heard this word before, hopefully. You commute to work. So commutative is related to individuals moving around. So if the 7 and 8 move and it stays the same, that's commutative property. And addition is 8 plus 7 different from 7 plus 8? No, they're the same. Individual things moved and they stay the same, that's commutative property. I like it. So multiplication and addition have this property. But what about division? Good Lord, it's bad. Even bad for me, which is really bad. Is 8 divided by 2 the same thing as 2 divided by 8?
No.
Some of you would say yes, it's a little troubling. 8 divided by 2 is 4. 2 divided by 8 is 2 over 8, which is 1/4. Yeah. So division, no, does not have this property. How about subtraction? Same idea. 8 minus 7 versus 7 minus 8. Not the same. One's 1 and the other one's negative 1. I like it. So only multiplication and addition have this property of commutativity. It ends up that it's the same idea with associativity. So what the hell is associativity?
I thought it was associative.
They know each
No. Individuals commute, parentheses associate. Oh shit, that's the little thing I've come up with to try to make it easy to remember.
So what did you say?
You ready?
Yeah.
Individuals commute. When I see a single thing changing places or moving somewhere, that's commutative. When I see parentheses get up and have something else inside of them, that's associative. So what the hell would that look like? I don't know. Oh yeah. The 4, the 7, and the 2, they're all in the same place, are they not?
Yes.
Yes, the 4's first, 7 seconds, 2's third. No individuals moved. What actually got up and moved? Parentheses. So that's associative property. Associative property means when I have all addition or all multiplication, it doesn't matter how you group them together, the answer will be the same. If you don't trust me, 4 plus 7 is, plus 2 is 13. 7 plus 2 is,
9.
plus 4 is 13. Of course they're the same thing, right? You can add, they basically say the same thing. They both say you can add and multiply whatever order you want to, but they say it in slightly different ways. Yes?
So just kind of like an easier way of saying it, it's just, there's parentheses, it's associative, right?
No.
I'm glad. I love you, man. You provide me with perfect segues. There are parentheses there, right? But what moved?
The numbers inside.
Individual numbers moved, so that would be commutative, right? Did the parentheses get up and move?
No.
No, they're in the same place. So it's not associative. Will it give you a problem like this? Oh, of course it will. Right? To really test to make sure that you're not just thinking that, right? So be really careful. It's associative if the parentheses in the problem actually get up and contain something else. And it's still the same answer, right? So, for example, 2 times 3 times 4 is the same thing as 2 times 3 times 4, like that. That's very true. This is 2 times 12, 24. This is 6 times 4, 24. Of course, they're the same. Now check it out with division and subtraction. What about this? Look at it. All right, let's try this out. Do these two. See if they're the same or not. It's gonna be like a little earthquake. Oh my God. Now, of course, I'm hoping you're able to do this in the right way. Here, doing the parentheses first, 7 minus 4 is 3. Here it's 8 minus a negative becomes 8 plus 3 is 11. They are not the same. So subtraction is not associative.
Wait,
Or I thought this.
it's not?
No,
What is
subtraction is not. It's just not associative. So I can. These both say the same basic thing. They both say I can multiply and add any order I want to, and it will come out to be the same answer. Right? If I have only addition or only multiplication, I can do it whatever order I want to. We should all know that. Okay. But subtraction, hell no. I can't just subtract any order I want to and have it come out the same. I can't. Right? And the most basic one is 7 minus 8 and 8 minus 7. They're not the same thing. So it's going to extend to trying to move parentheses around also. So here, if you try division, like that, right? So this one would be 16 divided by 2 is 8. Divided by 4 is 2. So 8 divided by 4 is 2. This is 16 divided by, what's 2 divided by 4?
2. Oh, wait, no, it's 1.
1 half. 2 over 4, 1 half.
Yeah.
How do I do division of a fraction? 16 times
2 over 1.
2, which is
Or 2.
very different.
Yeah.
And let me see if I can get you to understand. Stay with me. Here I'm dividing by 4. I'm dividing this number by 4, right? So I'm chopping 16 down and then I'm dividing it by 4. Here, I'm starting with 16. I'm not doing anything to it first. It's staying big old 16 and I'm dividing it by a very small number. So division and subtraction are not commutative or associative. They're neither one. But addition and multiplication all day. I can add and multiply whatever order I want to. I'm not sure how else to say it. Yeah.
So, subtraction is not associative.
Good.
Alright.
Yeah. Yeah, we saw that.
I just clarified.
Yeah.
Alright.
Yeah. Right here. Yeah,
But it's
subtraction is neither one of those.
But it's not,
Division is neither one of
It's
those.
not commutative.
Yeah, it's not commutative either. I love it.
So what would we write about those? Nothing?
Nothing. Yeah. So the real kind of question you would see. This is me just trying to give you a complete picture here. The real question you would see is, name this property, right? Here's the question you would see. Name, that's the most boring game show in history. Name this property. I can name that property. Of course it does.
The first one.
So if you think it's associative, did the parentheses get to move? What moved?
The numbers inside.
The individual numbers, so that's commutative, because individuals like we are, we commuted here. I don't think anyone lives in this room, thankfully. If you do, I'm sorry. I'll go get help. And there's better rooms on campus too. You wouldn't do the problem, you understand? The question is not simplify. It's just name the property, so you would just say commutative. And I love that commutative somehow becomes commutative with an N there, like you're suddenly back in the 70s or something trying to start a commune. No, commutative. That's a T there. Yes, I'm not going to have a question about subtraction because it doesn't follow the property. So I think you're all worried about something that's not even going to come up. There might be some questions related to subtraction and division that would be at the end of the section or something. So what about this? What property is this? What you got, Jeff? Now that one is,
No.
that one is associative because the parentheses got up and moved. Bam. That one is associative of what? Let's really be specific. Associative of multiplication. This one would be commutative of addition.
So do we have to write that too?
If you don't, I won't take any points off, but you should.
So when you say name this property, it's gonna be one of those, it's not gonna be.
Yeah, well, or it could, of course, be the other one we just talked about. That one's really obvious. Yeah, distributive. Yeah. That one is like, you can't mix this one up, hopefully. This is where something actually happens, something gets put together. These are just reorganizing things, right? Distributive is actually kind of doing something. It's the only property is really doing something. Instead of just moving stuff around.
So if number 2 didn't have the multiplications by or the 3 times 7.5, if it was just 3 next to the parentheses.
This is not 7.5, right? This
Or
is
excuse
all.
me, 7 times 5.
Yeah.
So if you took those 2 dots, the one by the 3 in the parentheses.
Well, this one has to
and
be
then
there.
The one
This one
outside.
has to be there. This one doesn't have to be there
So if
because
that
it's.
wasn't there and it wasn't there on the other side, it'd be distributive.
No, it's still. No, okay. Distributive property
Uh-huh.
is a mixture of a multiplication and addition, right? Distributive properties want to have an addition problem or a subtraction problem for that matter, right? Some kind of a little expression. And that whole thing is being multiplied by something. So it's how multiplication interacts with addition. So it's got a certain look to it. And of course, this piece could be as big as I want it to be. It could be 12 times a plus 2b minus 3x plus 5. And what would you do? 12a plus 24b, just distribute it to each piece. So the second thing can be as big as it wants to, and then the idea just holds. You just bring that thing through. So the distributive property has a very distinctive look. You should be able to find those quick. It's the commutative versus associative that you got to slow down. Say, there's a parenthesis there, great, but what actually got up and moved? Now, at the same time that this is not like the most crucial thing anywhere near in this class, it's also somewhere you don't want to lose points, right? So just kind of, I try to give you little triggers to make this quicker, to identify which is which. Okay. Let me see if they throw anything else weird at you. Nope. Oh, here, let me ask it this way. What if I said this? Use the commutative property to rewrite this. Well, that's a little evil, I know, but oh well, too bad. Use the commutative property to rewrite that.
7.
Oh, wait. Somebody stop yourself. There's 2 different answers I would accept. One of them is a little bit strange. I would not accept any 21 plus 7m's because that's using what property? Distributive. I didn't say use distributive. So the most obvious way to do this, who's got an answer for me?
I got one, but I don't know.
Yeah, right.
What's that?
7 plus 7 in parentheses.
No.
I think it's...
Is it 7 and parentheses and then n plus 3?
Yes.
That's the most obvious.
3 plus m is the same thing as m plus 3. Yep. So commutative property is all about either addition parts moving or multiplication parts moving. You can't move an addition and multiplication part. That totally changes things, right? The other answer that's a little weird, do you see how that's commutative? Everybody see how that's commutative? What actually got up and moved? Those individual things did. There's commutative property. The other acceptable answer is the one that I would be really interesting to get.
Is it?
This is 7 times something, right?
Yeah.
Could you, no, would it be?
Fence.
Yeah, that's
Yeah.
what I was about to say. Yeah.
So this is commutative property of addition. The things we're adding and they're still adding, somebody just turn around.
I was going to say that, but I got confused because it kind of looks like the parentheses moved, but they didn't.
They didn't
Same
because
numbers are-
this is a number and this is a number. So I moved the 7 there and I moved this number into the front. I just switched those numbers.
I was afraid to say it.
The parentheses still have the exact same things on the inside, right?
Yeah.
So they didn't move. They're not covering different things. And again, please, dear God, understand. I mean, this is just where you start to play with this shit too much and you're all like, oh God, what's important? This isn't horribly important, but there are some problems that aren't quite this ugly that they ask you. So they're going to give you a problem like 4 plus 5 plus D. Use commutative property to rewrite this. So what's one way you can rewrite it using commutative property? Yeah, 5 plus 4 plus D, 4 plus D plus 5, D plus 5 plus 4. I mean, just take 2 and move them. That's commutative property. See, that's going to be in the homework. I just want to give you one that was a little more... They have one sort of like that one in there. Okay, maybe. So commutative, individuals. Associative, parentheses actually getting up and having different things inside. Distributive, you should know. You got to know that one. That's the one to look for first, right? Because that's an obvious one. Yeah, that's what we got so far. What about?
So for the associative one, the actual parentheses have to move and the numbers inside have to be switched.
Oh, associative would be this.
Yeah.
So see how 375, the numbers really didn't go anywhere? It's just that the parentheses are containing different things. So officially this would be 3 times 35, right? Look, this is officially 3 times 35. This is officially 21 times 5. Right? They're both 105. So they are equal to each other. Right? I don't know what to say to you. So these parentheses, they got up and they moved here. That's what they did. So that's associative. Associativity, parentheses associate, individuals commute. That's the best little saying I can help you with. It's enough of that. Right? Let's get off of those properties. Spending a little too much time on those. Either you get that or you don't. You know, that's the way a lot of things are. This is just a definition, by the way. And really, again, at the heart of them, they just say, I can add and multiply whatever order I want to. I cannot do that with subtraction and division. I can't divide and subtract whatever order I want to. 7 minus 8 is not 8 minus 7. 8 divided by 2 is not 2 divided by 8. Yes?
If we don't put like commutative addition or stuff like that, do you see consequences?
No, like I said earlier, it would be nice, but I'm mainly looking to see if you can identify the property itself. But to be complete, it's commutative of multiplication or associative of addition. Yeah. So I just put a little note, but I probably wouldn't take points off. Probably. Let me see if they have anything else freaky in here. Always, right? Let's see. So how would I use associativity to rewrite this? Associativity.
You do 7 on the outside. I don't really know.
Use associativity to rewrite this.
Move the parentheses to the front.
What are they going to have inside now?
And 7.
5.
5 and 7. Here's that. See, 5, 7M. 5, 7M.
Yeah.
So no individual things moved, but the parentheses got up and moved. That's it. See, that's all it is. And I know right now it seems like... But it is a property of real numbers. There are numbers that don't have this property. There are number systems that don't have this property. So we're studying the real numbers. So for completeness, we want to talk about what they do. They have this property. Associative, they have the commutative, they have the distributive. It's not true for every set of numbers that we could use.
I feel like you could be mixing all everything around.
Yeah.
Staying the same.
The spaghetti property just... Let me see. Okay. Yeah, good. So there's not too much. Oh, I did. Oh, wow. 7.3 is only about distributive properties, so we basically have already done that one. I like it. Chilling. Let me do a couple more things, and I'll let us out a little early today. So if you need to go lick your wounds from the test, you can. start making corrections, whatever.
I don't know.
So guys, just a couple quick little things. There are actually some things called in math called identities. So they are related to operations. So addition has an identity. What the hell would that be? So what is your identity? It's who you are, right? So an identity, an additive identity, would be a number I add to something that does not change that number's identity. It doesn't change the number. What do I add to something and it actually doesn't change?
Zero.
Zero. So the additive identity is 0 because x plus 0 equals x. It does not change its identity. Please understand, on one level that sounds really silly, but again, the number system we use, that's true. For a different number system, it could actually be a different thing. So this idea of an identity goes beyond our own number system, right? Thankfully, in this class, we're just going to stick with our number system. So what's the multiplicative identity then?
1.
Yeah, because what do you multiply something by to maintain its identity? 1, because x times 1 is x. Now, something that goes right along with that, this is the last thing we'll talk about. You have to talk about this first, and then the next piece is going to make more sense. We have identities, additive and multiplicative. And then we have inverses. So an inverse of a number, an additive inverse, would be the number I add to something to make it become the identity. So if I want to translate that, if I have 7, what do I add to it to make the answer 0? Negative 7. And that word inverse does mean opposite. But if I just say, what's the opposite of 7, there are actually 2 different kinds of opposites. Right? At least 2, but 2 right now we'll talk about. One of them is the additive opposite, the additive inverse, which is just put a different sign. So what's the additive inverse of negative 11?
Positive.
11.
Yeah, positive 11. So these are additive inverses of each other. You just change the sign. Okay, that's awesome. Because when you add those together, they become the identity. So what must be true about the multiplicative inverse? Given a number, it's something I got to multiply by, so it takes it to... No, that's the additive. 1. That's the multiplicative. Multiplicative. What's in this? So what do I multiply 4 by to make it become 1? 4 times 1 is 4.